Today we are going to discuss furthermore about the mechanism of nucleophilic aromatic substitution. Last time we talked about two kinds of mechanisms which nucleophilic aromatic substitution should show you. These were addition elimination and elimination addition mechanisms. I mentioned the second one only and we discussed the first one, that is addition followed by elimination. We discussed important points regarding the first mechanism, and a few of its aspects are still left, so we are going to continue with that. As you know, we discussed about the two steps and found that there was a carbene ion formed as an intermediate in nucleophilic aromatic substitution in the first step, which was the slower and the rate determining step. In the second step, which was the faster step, the ultimate formation of the product took place. Now let's go on discussing the effect of substituents on the reactivity of nucleophilic aromatic substitution. As I told you that carbene ions will not be produced easily unless your aryl halide, as we talked, they are quite less reactive towards nucleophilic aromatic substitution, especially if you compare their substitution with alkyl halides. But nonetheless, they do undergo these reactions under somewhat strong conditions, drastic conditions, but this reaction is greatly facilitated if some electron withdrawing group is attached. Now the electron withdrawing groups, you know these groups, these are like nitro group or cyano group, etc. Not only do these groups they help in the reaction, their number, if it increases, if there is only one such group, then the reaction will be accelerated, but if two groups are there, the reaction rate will become much higher. Not only this, but their orientation also matters, like whether they are present at ortho position, meta or para with respect to the halogen atom. So we are going to find why this happens. First of all, if you look at this, then the presence of nitro or cyano or carboxylate group, etc., you can see here, they facilitate this nucleophilic aromatic substitution. On the other hand, if electron releasing groups are there, such as OH group or maybe NH2 group, they have the opposite effect. That means that they will be retarding the reaction. Let's look at the mechanism once again. This is the aryl halide present here. This is the nucleophile, and in the first step, when this carbene ion is going to be formed, there is going to be a negative charge present on the benzene ring, which will be dispersed over the whole of the ring, as we had seen earlier by writing the various resonating structures for the aryl halide. Now this X and Nu being attached to the same point and the negative charge being present on the carbon atom of the aromatic ring. Now the factors which stabilize this carbene ion, they'll increase the ease of formation of the carbene ion. And the carbene ion, of course, it's common sense, it's common logic, that will be stabilized by electron withdrawing group, because they'll be dispersing the negative charge of the carbene ion, and hence they'll be stabilizing the intermediate carbene ion. On the other hand, if electron releasing groups are there, they destabilize the carbene ion by intensifying the negative charge present on the carbene ion. It's not difficult to understand that if negative charge is intensified, then that carbene ion will be destabilized, will be having higher activation energy, will be formed with difficulty, and therefore the rate of reaction will fall. So electron withdrawal or electron release greatly affects the rate of nucleophilic aromatic substitution. Now this electron release or withdrawal, it may take place through either inductive effect or resonance effect, or maybe a combination of both of these. Both of these effects may be taking place, maybe functional simultaneously as well. For example, if you look at these cases, here you have got this molecule aryl halide in which nitro group is present on the para position. You can see that, and this nucleophile, when it attacks this aryl halide, results in the formation of this carbon ion here. Can you see the carbon ion? Cl and Nu, negative charge present here, and nitro group on the para position. Now this negative charge, of course, we can write the resonating structures and will be dispersed over the whole ring. This is the first case. Second case, that is for the reference, that is for comparison, that is simple aryl halide, in which when nucleophilic attack results in the formation of carbon ion, it's a normal carbon ion in which there is neither an electron releasing group nor an electron withdrawing group. In the next case, however, there is present a CH3 group at the para position, and you know that CH3 group is an electron releasing group, hence it releases the electrons over the aromatic ring, over the carbon ion, and the carbon ion which results is like this. Now this nitro group, which is electron withdrawing, it stabilizes the carbon ion, no doubt, and carbon ion 1, which is formed in this case, will be stabler as compared to the carbon ion 2, which is this normal simple carbon ion. On the other hand, the carbon ion 3, which is formed from this molecule in which CH3 group is electron releasing, destabilizes the carbon ion, it will be the least stable of all. So shows that 1 will be most stable, followed by second, and third will be the least stable as it intensifies the negative charge. Therefore, in this case, that is in the third case, the reaction will be taking place only under drastic conditions. In the first case, the reaction will be the easiest to carry out. So such is the effect of groups electron withdrawing as well as releasing towards nucleophilic aromatic substitution. As I told you that not only the electron release or withdrawal, that is the electronic effect, but also the orientation of these groups also matters as far as nucleophilic aromatic substitution is concerned. Electron withdrawing groups, they exert their greatest effect when they are present in ortho and para positions, and not when they are present in meta position. Let us see why this happens, and that can be seen by writing the various resonating structures. I am going to show you the resonating structures in each case. That is, in the first case, look at this structure very carefully. The carbon ion I have written with orthonitro-chlorobenzene. The molecule is orthonitro-chlorobenzene. Nucleophile has attacked this molecule. Nucleophile is attached here. First step, that is the addition step, resulting in the formation of this carbon ion here. This carbon ion with the negative charge present on this position. Here, ring is no longer aromatic. What happens next is that this negative charge moves on to the ring. It goes down there at this position, and in the next structure, this negative charge moves further, goes on to the carbon, again look carefully, goes on to that carbon which is bearing the nitro group. आपको क्लियर है कि ये जो नेगेटिव चार्ज है ये अब उस कार्बन पे प्रेजेंट है जिस पे डायरेक्टली नाइट्रो ग्रुप अटैच्ड है. इससे क्या होगा? What difference will it make? As you know that nitro group withdraws electrons, therefore it will accommodate this negative charge onto itself in this manner, giving rise to an additional resonating form. So overall, it is now clear to you that in this case we obtain 4 resonating structures, namely 1A, 1B, 1C and 1D. This 1D structure which is formed is an extra structure which is there because of the accommodation of the negative charge onto the nitro group. So this is the carbanion which will be formed in orthonitrochlorobenzene. It's a resonance hybrid of 4 structures. Next, let's take up the case of para-nitrochlorobenzene. The carbanion formed from para-nitrochlorobenzene is like this. That is structure number 2A. Here the negative charge which is present here again moves in a manner in which in one of the structures the negative charge comes onto that carbon which directly bears the nitro group. Hence, nitro group can accommodate this negative charge, giving rise to one more structure, one additional structure. The structure is this, that is structure number 2D, which is the extra structure being formed in this case. So, structure number 2A, 2B, 2C and 2D are the 4 resonating structures which are formed in the case of para-nitrochlorobenzene. In the case of meta-nitrochlorobenzene, however, the situation is somewhat different. Here you have got this molecule which is the meta-substituted aryl halide. Carbanion formed in this manner again. Structure number 3A. This structure 3A further give rise to structure 3B, normal structure, and then structure number 3C, again a structure in which the negative charge is present onto this carbon, which goes on to show that there are only 3 resonating structures possible, as in this case there is no such situation in which the negative charge goes on to that carbon which directly is attached to the nitro group. यहाँ पे कोई ऐसा स्ट्रक्चर पॉसिबल नहीं है जिसमें कि नाइट्रो ग्रुप उस नेगेटिव चार्ज को एकोमोडेट कर सके, क्योंकि ऐसे कार्बन जिस पे नाइट्रो अटैच्ड है मेटा वाला, उस कार्बन के ऊपर नेगेटिव चार्ज नहीं जाता है. So, which means that carbanion in meta-nitrochlorobenzene is a resonance hybrid of 3 contributing structures only. So, are all these structures clear to you? If these structures are clear to you, that means that you now understand that in the case of ortho-substituted chlorobenzene and para-substituted chlorobenzene, extra stable carbanions are being formed. Hence, the reaction gets faster. But in the case of meta-nitrochlorobenzene, only normal 3 structures are possible, which means that the reaction will not be accelerated that much because the carbanion is not that stable when we compare it to ortho or para substituted molecules. Hence, we can show that electron withdrawing groups, if they are present in ortho or para positions, they enhance the rate of reaction to a much greater extent as compared to when they are present at meta position. Similar will be the case with electron releasing substituents as well. Their effect will also be more pronounced when they are present at ortho and para positions. So, this completes the discussion about the first mechanism and also the influence of substituents onto this nucleophilic aromatic substitution, its rate. I'll see you in the next video.